Okay, welcome to the fluid module. There are several things that we want to talk about and lots of applications to fluids. We're not going to get into the big mathematics. If you're going into health professions, depending on which profession you went into, you'll get into the mathematics a lot there, but I definitely want to introduce the concepts because you experience the concepts all the time, and we'll bring in some of the mathematics to kind of help explain it. So first, what is a fluid? Okay. So if you think of a fluid, a lot of times you want to think of liquids, but fluids are liquids and gases. So anything that takes the shape of the container it's in. Okay, so air, water, beer, all of these things are fluids. Okay, so plasmas, anything that's going to take the shape of the container that it's in. So what are some ways that we describe fluids? So a couple ways we describe fluids are density, pressure, are probably two of the biggest ways that we like to explain and describe fluids. So let's look at both of these. A lot of times people use the Greek letter rho for density. We know, or you probably know, rho is equal to mass over volume. So you'll see rho is equal to m over capital V. So what is density though? So a lot of people say, well, the heavier it is, the more dense it is. Well, that's not necessarily true. So let's take a piece of paper. So if I have a piece of paper and I rip it apart. So there's piece A, there's piece B, and there's piece C. So which part has the greatest density? Okay, so think about it, write your answer down. Which piece, A, B, or C, is going to have the greater density? Well, they actually all have the same density. Because they're all the same material. So density is really the explanation of how much material is packed in a volume. If it's the same material, you have the same density. So the, size, as far as volume alone, is not going to explain density. Mass alone is not going to explain density. It's a combination of. And just some quick reminders over volume. Volume of a cube or a cuboid is equal length times width times height. Volume of a cylinder. So we have a cylinder, looks like that, with some height h, radius r, is equal to h times pi r squared. And then the volume of a sphere equals 4/3 pi r cubed. So three objects that you probably want to be familiar with as when calculating volume. So we have density equals mass times volume. Now a lot of times, especially in chemistry, they like to talk about what's known as weight density. And that is equal to the weight divided by the volume. Okay, so remember density is equal to mass over volume. So it's just a matter of, are you talking about the weight per something? So when you're looking at units, like if you had newtons per cubic meters versus kilograms per cubic meter. So that's how you would tell the difference between, or pounds per cubic meter, or pounds per cubic foot. So that's a weight density versus mass per cubic meter. So a lot of times in chemistry, again, they like to use weight density. Depending on your career, you're going to use pure density or weight density. Now pressure is where we really want to spend a lot of time with. That's going to be a capital P. So I want you to find a book and take a book and in your hand, let me have your hand, and I want you to hold the book flat. Okay, so hold it flat, and then take the same hand, I cannot draw, and hold it up on the edge. what does it feel? So we have it flat and we have it on the edge. Does it feel the same? And they do not feel the same. This is going to feel heavier, but in reality, is it heavier? Well, heavy depends on the weight, okay? So they have the same weight. Whereas pressure is equal to force over area squared. Oops, not squared, just area, force over area. Apologize for that. Got ahead of myself. So in this case, it would be weight per area. Well, when it's on its edge, its area is smaller, so it's going to create a greater pressure point. So if you think about a needle hitting a balloon, that's going to be a greater pressure point. If I can take a pencil to a balloon versus a needle to a balloon and apply the same force, the needle is going to apply a greater pressure because it's a smaller area. So we're going to look at that. So remember, pressure is force over area. So that's going to be something to kind of remember there. So how we can apply to some things. So let's look at high heels. So if someone wears high heels, so you're putting all of your weight on your metatarsals right here versus tennis shoes or flat shoes. You're putting your whole weight over this area. So your weight or the forces are the same. So now the area for the high heels is less than the area for the tennis shoes. So that means the pressure on your metatarsals for the high heels is much greater than the pressure on your entire foot for the tennis shoes. So that's why, if you read the articles, don't believe what I say. You read the articles, there are issues with people who wear high heels all the time, the pressure that's on the metatarsals and the damage that can be done to the metatarsals. So going to the flat shoes, just saw that pressure points going through there. I'm going to post a video with a bed of nails. And I want you to look at how it's going to work. So I want you to actually see this, watch the videos of an actual bed of nails. Because if you would take and step on one nail, if you weigh 100 pounds, that nail is going to push back with a 100-pound force. Versus if you are 100 pounds and you have two nails, so each nail is going to be 50 pounds. So what would happen if you have 100 pounds? So if you got a 100-pound weight and you have 100 nails, that means each nail is going to equal 1 pound force on your body. So think about this as you're looking at the bed of nails and why it's safe. So we're going to go through and kind of keep that in mind as we're looking at this. So one of the things we also want to take, so remember we talked about this weight density. So we know pressure is equal to force over area. Well, what about pressure for a liquid? So if I look at this, we know that density is equal to mass times volume, or density here is weight times volume. I can actually create a pressure for a liquid. So if we're dealing specifically with a liquid, we can either use this or we can use the pressure where you're going to get the weight density times the depth. So this is going to be key, like when building a dam, and how deep do you need to put that water with the dam? The deeper the water goes, the more pressure it's going to produce. That's why this is one of the reasons why. So we have arms, people, head. Sorry, people, I don't draw very well. So when they measure your really big biceps, sorry. When they measure your blood pressure, they try to get at the same depth or the same height as your heart. So they want this depth to be the same. So if they measure the blood pressure in your arm and it's at the same point as your height, or at the height of your heart, then they're measuring the blood pressure in your heart. So they're trying to get that depth to be the same. Well, some of you may be like, well, wait a second, how is this going to be the same as here? How is that equal? Well, remember we have weight per volume times depth. Remember volume, we talked about this, is length times width times height. That height is at depth. So I have weight times length times width times height, or some depth type of deal, was a cube for right now, times our depth. Well, those cancel out, so I get weight or force per area. So that's how you can go through and work through, and you're like, well, how would I know what to use? It's all going to depend on your application and kind of what's given. And again, a lot of times in chemistry, and I think even in some of the medical fields, they're going to use weight density times depth. You want to look at the depth, the location of the blood pressure cuff, or the whatever you're looking at. I'm going to provide some videos to kind of help you visualize why you measure the blood pressure at this point here. But those are going to be some applications that you want to see. So again, make sure you understand density and you understand pressure. Those are going to be the two fundamental things that we use to explain and describe our liquids. So in the next video, we're going to start introducing some of the principles that I mentioned in the discussion part, where we want to go through and look at some of these principles that govern how fluids move.